Hey everyone, we're going to talk about acids and bases today and why they react. So let's write it down. So the first thing we need to do is set up our page for Cornell notes. So I'm going to draw my line down the side and then two across the top. And then I've got my section over here where I put my name and the date. So right now it is 12/6/20. Might not be the date for you, but that's what it is today for me. So straighten the page up a little. Okay. So we're talking about acids and bases. So let's put that as our title. Acids and bases. And our essential question is, why do acids and bases react? Because it is definitely a chemical reaction that is happening when we put acids and bases together. So like baking soda and vinegar. Baking soda is the base, vinegar is the acid. And they react to make some carbon dioxide, lots of bubbles, and all this extra stuff. So water and sodium acetate, I think. So, but why does that happen? So that's what we're going to try and answer with this stuff. So first, let's do some vocab words. So we've got bases. That's my vocab word. And so when we think about bases, bases are going to be slippery and bitter and have a pH, which is the scale that we're going to draw later, greater than 7. So those are bases. A good example of this is soap. I don't know if you've ever put soap in your mouth or had to have soap in your mouth, but it is very bitter. Obviously, it's slippery. And then we think about it as a pH greater than 7. All right, so that's bases. Then we have neutral, which is obviously in the middle of bases and acids. So that's a vocab word. And this is just going to have a pH of about 7. And that would be like water. Water has a pH of about 7. That's our example. And then finally we have acids. Now acids have a bad rap. I feel like people think of those eating people away, or like you spill acid on yourself and you have to go to the hospital or something. And that's true. It's definitely could be dangerous, but bases are just as bad. And we'll talk about why in a second. But anyway, acids are typically sour. So malic acid or citric acid are one of the ones that you would find on like warheads or in any sour candy, really. So that's why it's sour, is because it's got acid on it, or fruits and stuff. So this is going to have a pH of less than 7. So the lower the pH, the more acidic it is. And I always thought that that was kind of backwards for some reason. I always thought it was a big number, it's going to be a really strong acid, but it's actually the opposite. The bigger number, the stronger the base it is. Now, we have to be able to tell this some way besides tasting it or feeling it, because that could be very dangerous. And so we have this thing called an indicator. Indicator. And it actually tells us, or indicates, whether it's an acid or a base. So, indicates, or identifies, there we go, identifies whether I'm just going to say acid or base. All right, so now we have our scale. So bases are going to be at the top of this scale. So it's a really high number. It's going to be a really strong base. And in the middle, we have neutral, where it's kind of not really a base or an acid. It's just whatever's in the middle. And then acids are at the bottom. So we have like lemon juice, orange juice, gastric acid. That's the stuff in your stomach that digests your food. Bases, let's go back to that for some examples. But we have bleach. Some of you use bleach to clean or to like remove some colors from clothes, make it that kind of spotty effect. Soapy water is actually very basic. Ammonia, if you've ever had a perm, or sometimes farmers use that to put nutrients back into the soil, so you'll smell that ammonia smell. It's really very distinct and stinky, maybe it's a better word. And then baking soda is just a little bit basic, which is kind of interesting. Maybe that's why we can use it for that experiment, baking soda and vinegar, without being too worried, I guess. But anyway, the reason that bases and acids actually react with each other is because bases want to take a proton and the acids want to give up protons. And so they like complement each other. You could look at it the other way where like one of them wants to give up electrons and one of them wants to take electrons. And so it passes from one to the other. And if both of them want to do that, then it does it very quickly, and especially or specifically if they're on opposite ends of the spectrum. So if I have like ammonia and gastric acid, that could be very bad, or bleach even and gastric acid. That reaction would be very violent, and that's where you would get some dangerous reactions. So let's draw. I'm just going to leave a little bit of space at the bottom for our last vocab word. But we have something in the neutral, so that's in the middle. And then we have bases up top. And then acids at the bottom. So down here we have 0, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So 0 to 14. And then I'm just going to put a couple examples. So I'll put bleach and baking soda, because those are ones we are probably familiar with. And then down here we have water in the middle, I should say. And then urine. Ugh, gross. Let's do orange juice down here. Orange juice and gastric acid. All right, so we've got a general scale. So the higher the number, the more basic, and the lower the number, the more acidic. Okay, and then our last one is a catalyst. Catalyst. Now, a catalyst can be used in a lot of different ways, not just science, but a catalyst is something that speeds up a reaction. So I could have a catalyst in a war, or something that causes change to happen a lot faster than it normally would. So a riot or a bill that gets passed, that could be a catalyst for a lot of change. For us, with a chemical reaction, it just speeds it up. Speeds up a reaction without actually getting used itself. It just helps it move along. So speeds up a reaction without, so this W with a slash means with, and then out being used up itself. So I know you guys have heard of elephant toothpaste, because you've asked me about it 100 times. Oh, I spelled elephant wrong. Elephant toothpaste. And there's other examples too. But in elephant toothpaste, there's a catalyst that causes that peroxide to rapidly get rid of or produce oxygen bubbles, and that's what causes it to like shoot out of the test tube. So that's a use of this catalyst. It speeds up reactions. But that's actually it for our notes for page 21. I forgot to mention that at the beginning. But this is page 21.